Just sort it out. So yeah, the tutorial here, for those who are newer to ESIG, we normally do these tutorials before the main workshop. We kind of get into a little bit more detail, a little bit of background on some things. So we're going to talk about the kind of forecasting and market operations, particularly some of the newer resources. So I'll give a quick introduction to show the agenda here. I'll show the agenda here, and I'll talk about how just generally on forecasting some newer topics. I like spend 20 minutes or so. Then hand it off to Erik, who'll give a longer presentation talking through market operations issues, the how storage and hybrids and DER participate in markets, and then we'll have a break. We'll come back after the break, and Amber and Mark will join us for kind of a panel discussion, short presentations, and then we'll talk through some of the issues we talk about. So very much open for you all's questions and discussion. So feel free to jump in at any time. I think because it's being recorded, it's probably better to come up to the mic if you do have a question. And we'll take them at any time that makes sense, but certainly we'll have time at the end as well. So just really brief to kind of level set. I think most here are probably aware of a lot of these things, so I'll go through it pretty quick. But when we think about forecast uses, forecasting can mean a lot of things. We can forecast things happening 20 years out and forecast things a minute out. So when we think about the power system, we look at forecasting for years ahead for things like what to support things like what's the load going to be, what's the adoption of distributed resources or electric vehicles, how we got to build a system that can manage that, the generation, transmission, distribution, things like resource adequacy and transmission planning activities, aspects like even down to the nuclear fuel cycle and kind of production cost modeling type activities. Then as we get closer and closer, we're starting to make more operational focused decisions down into kind of asset maintenance and optimization of fuels, outage planning. And then into the kind of week ahead and day ahead, where really the focus of the rest of this session is going to be around operational decisions. That can be whether or not to turn on generation, whether or not to store energy, getting into things like transmission management, congestion management, and then into real-time kind of stability and control type issues. So that's where the focus of today is going to be, and in that kind of context with the markets. When we think about renewable forecasts and think about how we would classify those, this is from an IEC report that we put together a couple of years ago. A few folks from ESIG were involved in that. There's a bunch of different ways we can classify, and just to give again terminology before we get into the more detailed discussion here in a while, we think about timescales from minutes or intraday type forecasts to day ahead, kind of short term, and days to weeks ahead. All of those are used, and depending on the specific application, some of those might be more or less valuable than others. The spatial range, again, some people like I think Mark in a while will talk about the plant level type forecasts, and then we'll also need to understand what that looks like across the system. Could be large amounts of DER, it could be specific clusters of wind or solar plants. So the spatial range is important there. The type of data we use is also very relevant. We have seen, and there's been a lot of discussions at ESIG over the years around how best to use different sources of data. That could be historical data that you're training models on, or it could be the numerical weather prediction models that are typically used to do the forecasting, particularly as you look hours or days ahead. And then in terms of models, there's different ways we can develop the models, persistence, kind of more statistical models down through full physical modeling, and then things in between using combining statistical and physical modeling. And then I'll talk a little bit in a while about some of the different forms of forecasts, where we have traditionally always thought about forecasts as a point forecast or deterministic forecast, looking at what's going to happen at this time tomorrow, at this time in an hour's time. What's the output of a solar plant or a wind plant going to be, or the load across the system or net load across the system. But increasingly we're seeing that you'll never be able to predict those perfectly, so we need to start moving towards kind of probabilistic methods, and I'll talk a bit about what we mean there in a while, as well as event-based type forecasts may be another way to classify them. So just to kind of level set the forecast terminology. Another one here, when we think about forecasting, we're thinking about things like horizon, where how far ahead you're looking, the interval length in that forecast, and the run length, how long it's running for. That has to line up then, and we need to think about how that lines up with some of the system operations issues, whether that's the kind of day ahead scheduling, unit commitment type processes, down into economic dispatch and load following, and down into regulating reserve, AGC, governor response, those types of things. So obviously the terminology is a little bit different, and sometimes some of the big challenges are when people doing the forecasting side of things are producing forecasts that don't necessarily line up with the system side of things. And so that's something that could come up in the discussions here. Before we go too far, I do want to ask some questions to get a sense of who's in the room and the kind of level of expertise, so we know what we can kind of talk to. So first of all, who here would consider themselves more experts on the forecasting side of things? Raise hands. Okay. What about on the power system, market modeling side of things? Okay, so definitely a lot more on the forecasting side, which I think was kind of how we've been thinking about this. So your slides are good, Eric. And so do most people have a good sense of how forecasts are used in operations? Is that something people think that they've a good sense? Okay, less, yeah. Do you use forecasts every day in your job? Okay, most people. And then we'll get into some of these kind of emerging resources, hybrids, DER, storage. For those, have you been looking at forecasting? Is that a key piece? Are you more focused right now on wind and solar forecasts? Who's looking at hybrid plants and how forecasting brings up? Okay, so still a few, but less than the kind of more general use of forecasting. Okay, so that's helpful, I think, as we put some of the discussion together here. I'm putting this off not necessarily to talk about what EPRI is doing, but just some of the kind of key things that we see in the research area that are happening in forecasting right now, particularly things like behind the meter forecasts and the impact on load, and Amber's going to talk to that after the break. Understanding the performance and value of forecasts, and I have a couple of slides on that just to be thinking about that as well. There's been a lot of effort by DOE and others in the last while, and we'll talk more about it during the week. Again, probabilistic methods talked about later on today at the main workshop, but something we'll think of, and just generally looking at how we can improve forecasts, whether it's putting specific devices out in the field, using more advanced machine learning methods, other things that are kind of helping us improve forecasts is a big piece. So when we think about forecasting and we think about the kind of research that's being done at places like EPRI or others, really it's around how we can improve the existing forecasts using better data, better methods, and then how we integrate those. So how do we better operate the system? How do we make sure we're doing that in an effective way? How do we value what the forecasts are bringing so we can target improvements in the future based on those value streams? So when we think about performance, one of the things I think is important, this slide and the next one that gets into more detail, but really want to just illustrate the point here that performance varies widely across different forecasting types, but also across plants. And it's important to not think about, so here we show like mean absolute percentage error. That's a useful kind of summary metric to think about, well, what's the average error of a solar forecast? And you can kind of see in this was a trial we did a few years back with EPRI, and you can see 6 to 8% of the best sites with maybe more data there and more historical data, as well as they were just the sites performed better in general. They didn't have as many outages and other things. And then some of the other ones were newer sites with less data, they had tracking, which made it maybe a little bit more difficult for some of the algorithms, that kind of thing. So they had worse errors up into 10 to 12 to 14%. So the point there is that's already pretty high for a forecast. We're used to load forecasting as a far smaller amount. You can aggregate it, and once you aggregate that, it gets to a lower forecast. If you looked at all of these together, you'd have a lower average error. But the other thing is when you actually look at this, so not going to get too far into the details on this slide, but the dots there are each of them are a specific look ahead time forecast competition for a particular vendor. So if you go, each colored bar is basically a different hour of the day. And as you start on the left-hand side of that colored bar, it's a week ahead forecast. And if you go into the right-hand side, I think it's an hour ahead, maybe 3 hour ahead forecast. So you're getting closer, and you can kind of see within each that the kind of curve are showing better performance as you get closer to real time. But the other thing you can see there is this wide variety of actual errors, because while that might have that same plant might have a forecast error an average of 8%, you can see in the middle of the day it's a lot higher than that, even on average. And then in the worst cases, it can get pretty high, pretty significantly high. So we need to be able to kind of manage those larger forecast errors. Obviously, we want to do work to bring those down. There's a lot of good research to bring the forecast errors down. But we also need to start thinking about how do we actually accommodate those into the way we operate the system. So when we talk about market decisions in a while, we have to be thinking about when you're making those decisions, knowing that there's these types of errors to be observed. We'll talk later on. Do we have this arbiter that's going to be used to evaluate forecasts, and it's going to be a nice way of being able to continue to update, continually see the performance of forecasts. I don't want to spend time on that one. But when you think about some of the trends and where forecasts are going, this was some work we did last year to kind of just do a survey on where the lay of the land was. We think about solar, wind, and load as, you know, they're related, but they do have different focus areas. Obviously, solar, a lot around satellite imagery, deep learning type models, and models that don't require measured power data. Often you don't have that for distributed solar. Sub-hourly resolutions becoming more and more important, where we're trying to understand what's happening within the hour, and then probabilistic methods are important. Same thing for wind, probabilistic methods become very important. We're seeing a lot more focus recently on offshore wind and increasing, trying to think about how we better forecast for offshore wind. And then again, the kind of deep learning. And we're seeing that both in the actual commercial providers, what they're providing, as well as in the research community. And then on the load side, load has traditionally been a forecasting tool that's, you know, it's been around for a long time. I think I may have a slide showing EPRI's 20-something-year-old forecasting tool, neural network-based tool that for many years performed very well, but increasingly being challenged as we get more distributed resources on the system. So being able to increase that spatial resolution and get that kind of distribution level forecast. We're also seeing distribution companies, whereas in the past it was always done at the kind of bulk system, that's where you're scheduling and dispatching the system. You're now seeing distribution companies also use forecasts as well to make some of their decisions. So they're having to focus on it. It's a different type of forecast because it's far more local when you're thinking on the distribution side. So thinking about the various aspects, demand profile changes, whether it's COVID-19 and now remote work, we're going to start seeing far more things like data centers, other aspects like that. And then extreme events is becoming more important. We're seeing increased visibility of those widespread heat or cold events that, at least on the heat side, the models are projecting will happen more frequently in the future years. So being able to forecast all of those types of issues become important. The other big trend we've seen is more interest in days ahead and weeks ahead forecasts. We're seeing this for maintenance scheduling. It's becoming increasingly challenging to actually schedule maintenance on generation. Typically, you do that in the April, May shoulder months that got pretty tight this year in some parts of the country. So being able to actually forecast weeks out and say, okay, this week or these few weeks are going to be a good solar period or good wind period. That's a good time to do maintenance versus other periods will become more important in the future. And again, that's probably a more probabilistic type forecast. You're not going to be able to forecast hour by hour what's going to happen in a month's time, but you could at least get a good sense of whether you're likely to have a certain trends that might be able to help forecast and then do your kind of outage planning in that time frame. I mentioned the EPRI tool. I don't want to dwell on this specific tool, but it's relatively similar to what other tools are doing. And the reason I want to bring it up is just that what I mentioned earlier on, the forecast error, if you look down the bottom right, for load is a lot lower than what I showed for solar. And so we're having to move to a system that does have larger forecast errors. We can improve those, but I don't know if we're ever going to get them perfect. So what we really need is that flexibility, the market designs and the operational practices to be able to move around that smaller forecast error or that larger forecast error. Distributed PV, I think Amber and others will talk about this more in a while, so I'll skip through that. Probabilistic forecasts, just if they do come up in a while, I don't know how much we'll get into that, but just a kind of an autonomy of the forecast. You know, it provides more than just saying what's going to happen. You have all these other kind of uncertainty bands around it. This is some work we've been doing that I'll talk about later, but looking at kind of different threshold levels can help us understand, you know, how much reserve should I carry, or how much should I be scheduling against, what should I actually pick as the value I schedule my system against. So these types of forecasts, while as we'll hear on the kind of market side, that markets are still run very deterministically, we can start using some of the probabilistic information to inform some of the inputs to the markets and other things like that we can help operate the system more reliably. It does capture some of the kind of outliers. It probably ends up being more economically efficient, though right now any of the studies I've seen are relatively minor economic improvements. It really gives us more of that confidence around kind of situational awareness and can help us respond to extreme events, that kind of thing. Last thing I wanted to mention is around forecast value. I talked about this already as something that we need to think about. And as you're seeing how the markets integrate forecasts and use forecasts, thinking through, well, where do we get the value of that forecast? There's a number of ways we've done that, and both of them have challenges. One is just to actually look at historical forecast value. So how much did it cost to purchase reserves in the past year? And then if I improve my error by certain percent, that might save me that amount of reserves, and therefore I might make that saving. The problem with that is eventually that's kind of assuming almost a price taker model if you think about energy storage evaluation. So it's assuming that the forecast being better doesn't actually change the rest of the system and the way we'd operate the rest of the system. So what we've been looking at is, can you do detailed simulations to better evaluate the value of a forecast? The issue with that is actually just benchmarking that and getting all the pieces that actually happen in real world operations into a model. So it takes a lot of time, a lot of effort. But once you have that, then you can kind of say, what if we improve the forecast in this kind of performance, the late afternoon in a summer day, for example, let's improve the solar forecast. Does that have specific economic benefits? So I think there'll be more presentations talking about some of this here later today during the DOE discussion, but these are the different ways we've seen to kind of evaluate forecasting value. So it is widely used. Obviously, that's pretty obvious. We're coming to a meteorology session. Of course, we know that forecasts are widely used. Linking though the decision-making process. So as you hear about the way the markets are operated, thinking through how that needs to link with what the forecast can do, and linking what the forecast can do with how the markets operate becomes more and more relevant. Keeping decisions until later can help because you got a better forecast. Obviously, that has to be traded off against the fact that on the market side, you have to be able to make decisions at certain times to start generation or to be able to make day-ahead markets clear, those types of things. But it is increasingly complex. We're seeing more and more data, and a big piece of what folks are seeing on this is just how do we manage all that data? How do we process it? How do we store it? How do we use it? And a lot of it's going to move to this kind of probabilistic and risk-based methods. So focusing on the rest of the session then, Erik's going to come up here in a second and talk about the market side of it, and then Amber and Mark will talk about or give additional context on that. We'll have some discussion. So before I hand off, Erik, you can start coming up. If there's any questions, comments on this, any specific things people want to hear or see.
Okay, so covered the agenda here. So, first kind of getting into, what are the different market areas, and then talk a little bit about each one of these. Might be more basics for some of you, but just kind of wanted to get that through to start. So this is sort of some of the timelines, and I think Aidan had a couple different charts showing something very similar, but you have your long-term power purchase agreements, far in advance, your forward capacity markets, typically around 3 years in advance to procure capacity for a market region. Then you have in different regions seasonal or annual capacity markets, as well as your financial transmission rights auctions, typically a few months to 6 months in advance. And then you get to the things that many of us are familiar with, and where forecasts might be most well known and how they're linked today, our day-ahead energy markets and ancillary service markets into our real-time energy markets, and then of course following real-time our settlements procedure. And of course there's lots of variation in there across different regions and different types of products and things like that, but that's just sort of our general timeline around electricity markets. I like showing this table. This is something we do every year to kind of give a feel for how much money flows through some of these different products and different regions across the US. A lot of information on here, but I think it's always useful to see, and this changes every year, and sometimes significantly. In fact, I think you'll see some really big changes from if we look at the 2020. This is 2020 numbers here. And I think, if you looked at 2021, you'll see obviously some changes in ERCOT energy markets. 2022, some big changes in MISO capacity markets, et cetera. But a lot of the volume really is in the energy markets still. And those regions that have capacity markets are pretty substantial as well. And of course, there you see MISO, perhaps not historically. This year, that might change. Ancillary service markets, pretty fairly small relative to energy and capacity markets. And, it's a very important piece of the full electricity market set of products. But I think it's always kind of useful to see that those relative, sort of the quantity of, revenue being earned by resources or being paid by those that are allocated the costs, fairly small compared to energy and capacity markets. So I'm going to talk about each of those products really just very quickly, just because I think that'll help in when we get to some of the participation model discussion. So this is, a lot of the characteristics of, I'll go through energy, ancillary service markets, financial transmission rights, and then capacity markets, and just some of the key characteristics that are worth knowing about each one of these. So energy markets. Energy markets have bid caps when in those regions that have capacity markets that are typically substantially lower than what the value of lost load would be considered by most. And of course, this is changing all the time, and we've seen some changes just recently too. But in other markets that may not have a separate revenue stream from a forward market or a capacity market, may have those bid caps closer to the value of lost load, or even at the what is quantified as the value of lost load, such as ERCOT or in Australia. Forward energy settlement in the US, we have a 2-settlement system. Actually, California could be considered a 3-settlement system, but you sell your energy and buy energy in a day-ahead market, and then balance off of that based on how conditions change in the real-time market. And that's not the same everywhere. In Australia, for example, it's real-time markets only. And of course, there's lots of variations around the world with that. But some very important characteristics of why that 2-settlement system does exist. Locational granularity. Where's sort of the value placed on electricity and energy at what granularity? And of course, in the US, we have nodal pricing really at a generation node level, typically not at a load node level, and certainly not at a distribution or of course, customer and use customer level. But in the US, across all the market regions, we do price at a nodal level from that generation bus bar. In Europe, it's at a zonal level. So we aggregate and across maybe 1 to 4 zones per country, and that's the granularity of how pricing is done over there. Another important aspect is what we call multi-part bidding, or how many components to a bid are there for a supply resource that is offering into the market. In the US, it's standard to have 3-part bids, and those include energy, no load or minimum generation, so the cost just to be online, essentially, and then a startup cost. And so those 3 parts are included in at least every thermal resource that's participating in the market. And then in contrast, in places like Europe and in Australia, they use single-part bids. So you have to kind of factor in these other costs and include them in your per megawatt hour offer that's being provided into the market. So just a couple of these characteristics around energy markets that I think are important to recognize, and how they differ across the world as well. Ancillary services. So busy chart here, and the terminology here differs no matter where you go. And I won't get into, we don't have time to really get into each of the different components there. What I really wanted to show, so showing operating reserve, I think we're all familiar with operating reserve and a lot of different types of operating reserve as you look at those branching off from the left to the right. And then on the other side, you have all these other types of grid services, and mostly focused on the bulk system that are also very important grid services that are supplied by various supply resources. What I did want to show here in terms of, again, linking it back to markets, is how are these services really scheduled and compensated and paid for? And so as an example, these services here, there are competitive auction-based markets really in every region in the US today. Contingency reserve, regulating reserve. And then this next set of boxes here, there are competitive auction-based markets in some regions, but not all, maybe in several. There might be even some that are in one area. Maybe there's a competitive market in one ISO, one market region, and none of the others. And sort of, it's kind of an emerging way of compensating and allocating costs for these types of services. And then there's another category here of services that get cost-based recovery. So it's not competitive, but resources that supply this service get recovery for the additional incremental costs that are incurred from providing that specific service. And then there are other services that there's no cost recovery, no. So there's no competitive market, there's no cost-based recovery, and it's just something that's being provided inherently. So I think that's an important thing just to kind of get through, and this differs in all sorts of different regions out there. And what's important to recognize is, you might ask the question, well, why isn't the blue box on all of these services? Why isn't there just competitive market for every good service that we need? Isn't that the most efficient way to do things? And this is really just to show that there are very legitimate reasons that this differs, and reasons why a competitive market may not make sense, or maybe it doesn't make sense yet. And some examples are, maybe it's too complex to design this. Maybe the software is not quite there yet, or it's just too complex to really think through all the different design features. Might be that it's too specific to a local area, and it's not going to be competitively provided. It might be that the system just has way more of this aggregate service than is needed. If I'm getting, and of course it costs money to implement and administer these markets, and if I've got way more than I need of it currently without a market, is there a need to build a market? There's probably different opinions on that, but in terms of prioritizing, that could be another reason why maybe there isn't a market. And similar to that, it might be that the cost of the service is small enough that the benefits of administering a market may not outweigh the costs. And then could be more of a grid code, rather than a specific system need that is. So a lot of different reasons why there's variation there. Financial transmission rights. So an important part of the electricity markets today. Historically, before markets, and in regions that don't have markets, we had physical transmission rights, and we realized as systems moved to markets and least cost economic dispatch, we needed a change from physical transmission rights towards financial transmission rights. And just the example here that is kind of a good way to think of how they're used, and then how they may benefit folks that own them. So in this example, you have a congested transmission line such that the price at the generator that is supplying a large amount of the load on the other side of that transmission constraint is $10, whereas the load, all of the load is paying $50. And that price separation is happening from transmission congestion. And what happens in this case? So your generators are getting paid, the first generator is getting paid $1,500. The second generator is getting paid $7,500. And then the load is paying $150,000. So the ISO, the market operators, is the one that's collecting this and providing those payments to providing the payments and collecting the payments. And you look at this example, it's like, wait a minute. So the ISO is collecting $150,000, and then it's providing $9,000 to the generator. So the ISO pocketing all that money and going on trips and things like that. No, so that is money that's being provided to the owners of those financial transmission rights. And ultimately, that's getting back to consumers in terms of the auction revenue rights. And so there's sort of this two-part process where the transmission owners and the consumers that are under those transmission owners through the rate base are the ones that earn the revenues for selling the financial transmission rights or keeping them. And then there's other opportunities to hedge against transmission congestion by folks or speculate, as well. They can earn money, financial traders, by seeing some of the differences and earning money from those financial transmission rights. So a lot of different variations across the ISOs that I won't get into, but that's really kind of the gist of why these financial transmission rights exist. Hedging against locational price volatility, potentially speculation and earning profits from differences between financial transmission rights, pricing, and energy transmission congestion pricing, and earning that revenue. And then finally, capacity markets and resource adequacy. So that table kind of shows some of the different ways that different markets meet their resource adequacy today. And many of those are through capacity markets. And so, one of the things that we find is that when there are price caps and or bid caps that limit the price to something that's far below what the value of lost load, what consumers might be willing to pay for energy, then you don't allow, or in addition, you don't allow these conditions to happen very often because we don't want to have shortages occurring all the time. As well as these exogenous reliability targets. So if a region says, I need to have this much capacity built before I get to the year I'm looking at, that's a reliability target, and a way to get to that is potentially through a capacity market. And so those three things, or any sort of combination of those, are really what leads to capacity markets. And there's lots of opinions on current effectiveness of capacity markets, and you'll hear different thoughts on that. I won't talk about any of those today, but I will say that there's a lot of differences out there. But capacity markets generally have a uniform price, just like energy markets, based on the bid of the marginal supplier of capacity, typically through a going forward costs or new build costs if it's a new resource. And there's a lot of differences in terms of how far is being looked ahead, how performance is being compensated and quantified, how do you count the contribution of different resources and things like that. But this is sort of the, capacity markets, why they exist and where do they exist. So let me stop there, see if there are any questions before going on to the next part. And I think we may have time for questions at the end also, but.
Russ Forward, Polaris Systems Optimization. Thanks, Eric. Can you just comment a little bit about on the criticisms of the capacity markets? And there's a bit of a debate about that. And I have my opinions, but I'm not sure I fully understand why the capacity markets are so criticized.
Yeah, I'm sure there's other folks around that can give you their strong opinions, and I try not to give strong opinions one way or the other. I think I kind of covered why they exist, right? And I think that's pretty well understood. We don't want shortages to happen that might lead to these high prices that might be necessary to recover fixed costs. We don't want that to happen all the time. And for political reasons, we may not want, and we saw, in last February, very high prices for a very long time period. And there's very, very good reasons for trying to limit prices from being that high. And so that does lead to these capacity markets. I'd say the main criticism for capacity markets is how administrative they are. I think from a lot of the theoretical view is let's have, energy markets and marginal cost pricing works very well if consumers participate and everyone bids their marginal costs, that you don't have to deal with the fact that there's all of these very administrative components to capacity markets, things like requiring minimum prices into bids, how they count how much you're allowed to sell into the capacity market. Demand curves are very administrative, and that's something that we saw in MISO earlier this year. So I think I would say that's the main argument. I'm sure there's other folks that can share more of those, but I think that's probably what I'd say. And there's lots of benefits in theory if you have consumers participating in the energy markets, that can work very well, not need this separate administrative market. That's probably the best I can do, and we can talk later about maybe some specific opinions too. But
great, thanks. And I understand we're going to be talking more later about participation models.
Yeah.
Okay, great. Yeah. Thank you.
Okay, so this next part probably will be a quicker thing, but I think these are kind of some useful ways to link markets and forecasting together and sort of how that's evolving today. So we have all of these processes. Aidan had a chart showing some of the different, market and operation processes. And then we have some of these forecasts that are currently being integrated into, many, if not all of these different processes. And what I really wanted to share is that what we're starting to see is a new way of using forecasts today and different types of forecasts. And so on the bottom here are kind of other things that are being used into these processes that could benefit from having forecasts as their input. And so really what I want to show here is the change in how we're thinking of forecasts and how forecasts are being used in how to operate the power system and operate the wholesale market. So a couple examples. First is reserve requirements. So, we have a lot of research that's showing that you can forecast what the reserve requirement is, just like you forecast what the load is or what renewable output is. And using information to say, as the easiest example, if I use reserve in case a cloud comes over my solar field, should I procure that reserve at midnight? Right, so I know that there's not going to be a cloud issue at midnight. So that's a forecast that says, it's a pretty basic forecast, and you can see how that can get more complex, but you can use information to say, because of this information I have, I need more or less reserve capacity, and I forecast that reserve capacity just like I forecast other things. Same types of inputs can be used. So reserve requirements and forecasting. Another example is contingency analysis. So contingency analysis is really before the market runs, I want to see what types of issues I might have. What do I need to monitor? What facilities do I need to monitor on the system? And forecasts aren't really, haven't historically been used in contingency analysis in the past. Contingency analysis is really, I'm going to drop a transmission line and see what happens. I'm going to do this for every transmission line or a large set of them to see which of them are in danger of being overloaded or violating different limits. But with renewables and extreme weather events, we might see that forecasts could be very useful for input into my contingency analysis and the types of contingencies that I might include in my contingency analysis. Offers and how we participate in the markets. So of course, there's a lot of useful ways that forecasts can be used for offers and how that can actually help, and talk a little bit about how emerging technologies like storage and hybrid could use forecasts of prices, forecasts of renewables, and other things to actually include their, or to help their bid strategy. Financial players as well could use forecasts to help understand how they're going to participate in the market. And then finally, things like transmission limits and fuel limits. We're about to see some changes to have ambient adjusted line ratings across the US, and that's a forecast. So we're going to use forecasts of temperature to set our line limits, and doing that going forward. So having a forecast for line limits. You can even look at how that might affect things like gas pipeline limits and pipeline contingencies and things like that. I saw the battery message. Is it? We're trying to figure it out. Oh, that's right. Okay, so what was our break?
Well, 10:30 was the official one. So
10:30. Okay. Okay. So last part is really getting into kind of the theme that we had for today, and looking at these emerging technologies, and what I'll do is sort of focus on how these emerging technologies participate in market operations. So I mentioned participation models at the very beginning, and this is a term, I don't know, Amber, was it CAISO that coined participation models, or was it FERC? I can't remember who was the first one that started using the term, but it's pretty commonly used. Yeah.
I don't want to claim it and not be the one, so it may have been us when we were doing the two models.
So the couple definitions here, and that FERC had and put into some of its final orders, and they were saying participation models are the tariff revisions that consist of market rules that recognize the physical and operational characteristics of a resource and facilitates their participation in RTO or wholesale markets. We like to think of it too, we kind of add on that it also might include the market clearing software aspects of the technologies as well, which it does. But you think about this as, how does a wind resource participate in the market? They might provide different information. They might have different rules than a thermal resource. And there's a couple objectives that we'll talk about, but that's really what it comes down to. And what I'll do is kind of talk about a few examples of different participation models that are in existence today, particularly around emerging technologies. So what are some overall objectives? And I don't know if these are maybe mine or EPRI's. I can't remember if we took this from something else, but they're very in line with what I think an ISO or the FERC might have as well. And that is to allow for the greatest flexibility in participation options, but note the different perspectives of different market participants. So having flexibility that says, I'm not necessarily forced into this way of participating in the market, but there is this option that may benefit the system. It may benefit me as a market participant that I can choose to utilize. Actually some examples there of some specific ones there, but I'll kind of mostly want to focus on that last bullet that really looks at the fact that these granular models that represent the physical characteristics of a technology tend to provide efficiency gains. And that's, through plenty of research and analytics with plenty of caveats. But by having that granularity that sort of is able to represent a technology and the parameters that make up that technology has substantial sometimes economic efficiency gains, which could also be reliability gains as well. But they add complexity to not only the market software, but to the market design. They may not be desired by all participants. And one other thing that's not on here is they may also stray from our other objective as market operators of being as technology agnostic as we can, right? So those are some considerations that are very important. So on the one hand, you have some efficiency gains by adding this granularity of how this resource participates in the market, but I add complexity. I stray away from this technology agnostic goal that I have, and also it might not be the solution that everyone wants, and there's very good reasons for that. So that's just something to start to discuss before we get into some of the different participation models. So conventional generators have participation models, and they've had these for a while. I talked about 3-part bidding at the very beginning here in the US, and that is a part of the conventional generator participation model. They also have a lot of the parameters that are very specific to the operating constraints of a steam turbine or a combustion turbine, and even some that I'll talk about in terms of combined cycle facilities, things like ramp rates, minimum and maximum ranges, all these parameters that really show how I can participate in the grid, how much energy I can provide and get scheduled. So that really is making up this participation model for a conventional generator. Now, combined cycles, in addition to some of those parameters that might be in existence for a traditional thermal, steam turbine, I have other operating parameters because there's some unique characteristics for a combined cycle facility based on the configuration that combined cycle facility might participate in. This is just a couple examples. So a couple of the market regions have specific participation models for combined cycle facilities that they can use. And again, this is sort of that objective of, by having this configuration-based participation model where I can actually give the information on not just one facility, but the combined facility of the combined cycle, adding that granularity has economic efficiency gains, right? And that's why they were introduced in these regions. They have other complexities and other things. And in fact, the main reason why not all of the market regions have this is because they have computational challenges in being able to introduce these into their market software. So again, that kind of gets back to that first objective of why we have some of these granular participation models. So other technologies have participation models as well. So variable energy resources, of course, have weather-based operation. They use forecasts as input. They have different treatment in how they're used in the day-ahead market and where forecasts are used in the day-ahead market. They don't use commitment parameters. You don't have a minimum generation for a wind facility or a solar facility. And they also may have performance penalties waived because they're not controllable. And they also might not be eligible for certain products, for certain services. Battery storage is obviously very unique technology. It can inject energy and it can withdraw energy. It has an energy limitation through its state of charge, and different ways of how that state of charge can be managed, whether it's from the ISO, including that in its software, or if it's through the asset in its offer strategy. And again, no commitment parameters for that storage facility, but you have these state of charge parameters that might require additional telemetry, for example. Demand response is a resource, is a participation model that has some very specific rules in terms of when it's called upon, how it's settled, and might even have limitations on how often it can be called and things like that. And then finally, distributed energy resources, or maybe I should even say distributed energy resource aggregations have their own participation model as well in some cases, and that might allow for aggregation of multiple technologies. It might have all these other potential parameters that can characterize those resources. It might have things like how you factor in distribution constraints. Not today, it may not have that in the markets, but it might, in the future have parameters associated with the distribution system that might be part of how you operate those particular technologies. So electric storage resources, you'll see lots of acronyms here. We try to list them all on the bottom, but you don't really need to know them. Just that you hear a lot of these maybe terms in different market regions, but they really all are the same thing. This is the participation model for an electric storage resource in different regions. And it tends to be that there might be one participation model for continuous storage, like a battery, and then maybe a different participation model for binary or discontinuous storage, such as a pumped storage hydro that can't just operate fully from generation to pumping. But there's lots of other aspects that go into this, whether there's telemetry required for state of charge, how that state of charge is used in the market clearing process, the parameters that are necessary. FERC actually had a set of parameters that each of the ISOs had to include as part of the participation model, and other aspects, settlements and things like that are specific to that technology. One of the things that is typically part of this is they separate out the technology from the participation model. So in other words, a battery participating in the market may not necessarily have to use the battery or the storage participation model. There might be advantages for it doing so, but it may not be required to do so. So there has been some separation from the technology and the participation model, even though the participation model is modeled after that particular technology. Hybrid resources. I think we'll talk more about that in the panel as well. But adds another layer of complexity, because now you have two facilities that are interconnecting in the same location and can be operated potentially very differently than if each of those technologies were operating independently. So we're seeing now that there's kind of two different participation models for these resources. One being the separate independent resources, sometimes called the co-located model, sometimes called the 2R or two resource model. And then you have the single hybrid resource, or sometimes called the integrated hybrid or the 1R model, where the single resource, the ISO may not have the information or use the information in market clearing of each individual component of the facility. So it's almost like a black box to them, what's inside, whereas the separate independent or co-located model, you have the information, so state of charge of the battery, forecasts of the renewable component, all is information that can influence how it's going to be operated in the market. Demand response, again, different participation models. lots more acronyms in all the different regions on how demand response participates, but you can kind of put them into two categories. One being economic demand response, that is participating based on prices and earning revenue from the energy market, having to comply with net benefits tests and baselining. And then you have emergency demand response, which is really resources that are being called upon only during certain critical events. And this has a little bit more that I realize now this one didn't have the acronym list. Maybe we can add that later. But you'll see there's lots of different participation models in all the different market regions with some slight variations on rules and parameters and things like that. But what I also was describing here, which I think I'll talk about in detail for sake of time, but the fact that demand response resources in the FERC jurisdictional market regions get paid the energy price, right? So they're getting paid the LMP if they curtail. Now, if they curtail, presumably they're paying less as well, right? But they also get paid the LMP for their region when they're curtailed, but that's only if they pass this net benefits test. And the net benefits test is basically saying that by calling on the demand response, you're saving more money than, substantially more money than you would have otherwise, even with this additional payment. And pass this net benefits test, and there's just an example here on how that might work. Okay, finally, DER aggregation participation models. And of course, all these participants have different acronyms, different names, and different requirements. And it's honestly very, very hard to keep track of, as I'm sure many of you are aware of. But really what we've seen, and many of you may have heard of the FERC Order 2222, which was the order from FERC to facilitate participation from aggregations of distributed energy resources in the wholesale markets. And what this did is it said that an aggregation of DERs can include any combination of DER technologies. They don't have to be homogeneous. You can have an aggregation that includes electric vehicles, demand response, load type resources, typical, lithium-ion batteries, solar, microgrids, et cetera. All of that can be in one DER aggregation. What we saw is that some of the market regions introduced new participation models specifically for DER aggregations, whereas others said, we're going to keep ones we have, and these DER aggregations can use these existing participation models. And there were some differences in how they did that. But also lots of other differences on things like what services they're eligible for. Some cases, can they aggregate across transmission nodes, or do they have to be located in the same region or under the same transmission substation? They may have had size limitations. They may have said, look, if you're bigger than, 5 megawatts, you need to participate as your own resource and not in an aggregation, or maybe that the aggregation limit had to be a certain minimum or maximum, depending on things like whether it spreads across nodes and things like that. So a lot of other parameters. We do a lot of these tables that compare all the different participation models for all the technologies, just to kind of keep track of those and show the differences, and sometimes helps folks kind of have these at the ready to be able to compare them. But there's a lot of differences and a lot of good reasons for those differences. Of course, a lot of times this is from a FERC order that initiated something like this, but each region may have gone slightly separately in some of the details for very important reasons. Finally, I stole this diagram from Mark, and I think it's a very useful way of thinking about, maybe what the future of participation models are And that's this idea of a universal participation model, kind of thinking about, all the different parameters that might be necessary and allowing that to be how you might represent any technology, whether it's any combination of different technologies and the parameters that might be associated with that. And I think it's a very useful way of thinking about it. There are, of course, potential challenges. One being we might not necessarily know all of what the parameters of a new technology might be. Things like let's long duration storage, hydrogen. What are the parameters associated with that? Would that fit with this universal model? Can we think of everything that we might need now and build that in today so that we're not having to do sort of piecemeal incremental changes to each participation model as a new technology becomes economic and able to participate. Stakeholder priority is another thing, and how we prioritize these different participation models and how we include them. And then loss of efficiency in terms of maybe the granularities and whether we can include all those granularities, as well as computational issues, which are real. I know it's not something we hear of much, but if it takes 2 days to solve a day-ahead market, then that's not going to be a very effective day-ahead market. So lots of things to think about. So hopefully that was useful. So covering a couple of those different topics, getting into some of these emerging technologies, how they participate in the market, and yeah, definitely open up the floor for questions or comments, and feel free to comment on any of the things that we shared.
Back with a kind of a panel discussion. Amber from California ISO is going to start us off talking about some of the work they're doing and the experiences they're having. Mark will then talk about the view kind of from the next era or the developer side, and then we'll have hopefully plenty of time then for discussion. So feel free to ask questions. We'll probably wait until both Mark and Amber have spoke to really ask questions, and then we can get into some discussion. So Amber.
All right. Hi, everybody. We'll see if I stay up here. If I go, it's probably easier to see it down below. No, Mark's like, oh, you're standing right by me. Okay, I'll go down here. That way you can sit down. All right. So for the presentation today, I wanted to talk a little bit about some of the market participation models that Erik had teed up earlier. Two of those market participation models that the California ISO has introduced in the last couple years is the hybrid and co-located participation models, as well as a little bit of the resource evolution that the California grid's been going through in the last couple years. And then in addition, the renewable forecasting products that we have, and then some of what we're seeing of forecasting the new resource types and the new data requirements that are needed to forecast those resources. So the California Independent System Operators located in the western part of the United States, the BAA operation, where the California ISO operates the day-ahead market, as well as the real-time market, and then the reliability responsibilities, is the area within the light orange, California, a little bit of Nevada. We also operate what's called the Western Energy Imbalance Market, and that is throughout much of the WEC region. And we have a few participation groups coming in next year that are in blue, but the items that are in all orange are already participating in the Western Energy Imbalance Market. So I brought my laptop up here because we keep breaking all of these records. So by the time I put this out, we've already broke them. So we've hit a new solar peak of over 14,000 megawatts. And right now we're breaking that almost daily. So we'll probably continue to break that until we get to the highest sun angle on June 21st and see where we go from there. The new wind peak, it's been a while since we had a wind peak that was broke. So that was 6,200 megawatts. And then the new renewables serving demand, the amount of renewables that are on the system compared to the load that's there, we hit 103.5% on May 8th. And the one thing that's interesting about that day is we didn't just hit it for like one instantaneous second. We actually hit it for many minutes throughout the day, because we were riding right around the 100 before we got to the 103.5%. The steepest ramp that's on the system is 17,660 megawatts within a 3-hour time period. That's when the sun's setting. And then peak imports, about 12,000 megawatts. And our peak demand has been there since 2006. I will say we got close to hitting it a few years ago, right before COVID, but we didn't quite make it. We were just shy. Currently installed, so these numbers are as of November of 2021, so they need to be updated, but we're probably close to about 600 individual resource IDs on the system for renewable resources, totaling about 22,000 megawatts of capacity. And we have about 13,000 megawatts of rooftop solar on the system. So what's been happening on the resource mix side? So California has pretty aggressive goals to getting to 100% of energy by zero carbon resources. So by 2045, the goal is to be 100% of all energy is to be provided from zero carbon resources. With that, in 2030, an intermediate step is that we'll have 60% of that energy provided from a qualified renewable source. So this graph on the left is showing, do I have a, oh, okay. Showing growth over time. So blue is wind, orange is solar. This is 2014 for reference. And then this is the November of 2021. So you can kind of see how it's really been a steady growth of solar over the years. Wind has just recently started growing slightly, but it's holding a little bit more steady than on the solar side for the state. And then in total, we're at that like 23,000 megawatts. As for new resource types, I'll talk a little bit more about the definitions of them in a second, but there's two definitions. We have a co-located and then a hybrid, and these are the two technology type combinations. What we see is those technology type combinations are mostly solar and batteries on the system. We are seeing some wind battery on the system come, and we also are seeing some gas battery on the system. But right now, the dominating, even within the growth expectations, are for the solar battery combination. On the left, you see megawatt wise, we have a lot more co-locateds expected to come onto the California ISO system. So by the time we get into 2023, about the 6,000 megawatt mark. Hybrid resources, they are expected to start growing more than what we've seen on the co-located side, but not quite as much yet, where they're at, you know, by the time we get to 2023, about 800 megawatts on the system. This data comes from LSE. I try to avoid all the acronyms on slides, but they'll sneak in there. Load serving entity. So we have to do, the forecasting team does the flexible resource adequacy program annually. And within that, we collect data from the load serving entities about their expected build out. And this came from that survey this year. The other technology sources that we're seeing grow in the system, storage, energy storage. This is the large scale energy storage that's on the system, not the co-located energy storage. But what you see, this is looking at the charge and the charge profiles of those resources right now. This was March of 2021. The scale is the same. So the top part of the scale is 6,000 megawatts. But you can see that as of March of 2021, we have 500 megawatts of batteries on the system. And then fast forwarding to February of 2022, we're just over 6,000 megawatts on the system at this time. So that's how fast the energy storage resources have come onto the system in just a year. We are expecting some more megawatts to come on throughout the summer as well. So we will continue to see the growth in this area. This is the main resource that we're seeing growth on the system in conjunction with renewables right now. To talk a little bit about DERs. A lot of the presentations are going to be focused on the hybrid and the co-located resources, but I did want to talk about the distribution energy resources just a little bit. These resources are impacting the demand forecast, the load forecast that goes out. Right now, we have about 13,000 megawatts on the system of rooftop solar. There's two lines here. One of them is the forecasted capacity, so the megawatts that are on the system. And then the second is the forecasted max production. So you'll notice that the max production is a little bit less than the capacity that exists on the system, but we're expecting to see about 19,000 megawatts of rooftop solar on the system by 2030, which is not that far away. You can kind of see a graph of where the heavier capacities of the rooftop solar exist. They are similar in nature in Southern California, population dense areas, right in the Bay as well. But this continues to grow as we go forward. We're very close to the point where we have the same amount of rooftop solar on the system as we have large scale solar. Also growing behind the scenes is battery storage. So energy storage is growing on the front side of the meter, but energy storage is also growing on the DER space. So we have seen some significant growth since 2018 within the battery storage growth. A lot of that's concentrated down in Southern California, right along the coastal area, with some of it also within the lower Bay, San Francisco area. And all of these pieces, I could do a whole nother presentation on demand forecasting, but I'll save that for another time. All of these technology types are feeding into the demand forecast as a variable that now has to be accounted for in some way so that the demand model knows what's driving the load forecast changes in actuals and in future as you go forward. So I'm going to transition back a little bit. What is a hybrid resource? So for California ISO, and note that all of us are a little different in how we've defined them. A hybrid resource is a generating unit with one unique resource ID at a single point of interconnection with components underneath it that use different fuel sources or technologies. So a combo of a solar and a battery with one resource ID. That resource ID is the one that's participating in the market. We still get separate telemetry information. It's a requirement for us to get separate telemetry information for the hybrid. So we still have visibility to the solar resources output, the battery resources output as a requirement. Then you have the co-located approach. And this is a generating unit where you have a unique resource ID for each component. So you have two components, like a solar and a battery, but each one of them has a resource ID that is optimized in the market. And this allows the market to use the participation models that are there for it. So the solar resource can use the solar participation model. The battery resource can use the battery participation model, and then the market can optimize them together in harmony, hopefully. So the California ISO started the Hybrid Resource Initiative back in 2020, I think. We were talking about it a lot within 2019 as well. We had some phases of the go live. They're still going live right now. But phase 2 go live, some of the system components to hook up the hybrid are expected to go live this fall in 2022. That one really has some of the items under the hood for the hybrid resources. The phase 1 go live was in December of 2020. That was a lot of the participation components that were needed for the co-located resources. There's still movement and improvements happening for both the co-located and the hybrid resources, but that piece is expected to go in fall of this year. We are, like we saw on the previous slide, We're expected to have about 6,000 megawatts of combo renewable storage by 2024. And for forecasting services, the CAISO has put out right now that we're going to be providing wind and solar forecasting services is required for co-located resources. That's the same. We forecast for all of the wind and the solar resources already on the system. So we continue to forecast for the standalone co-located resources. It's optional for the hybrid resources if the ISO will provide the forecasting service or not. So when they go through the registration process, they can choose the ISO to provide that forecast for them or to do it on their own. What we are seeing is the majority of the hybrids coming on are still requesting the ISO forecasting service for the components that they have. The different pieces of benefits and dispatch and forecasting for hybrid versus co-located. So there's no aggregate forecast for the hybrid resource. We don't produce an aggregate forecast. That's the responsibility of the hybrid resource owner to do. We will provide a forecast for the component underneath the hood. So if there's 100 megawatts of solar, we'll provide a forecast for the 100 megawatts of solar to the SC, the scheduling coordinator, and then they choose how to use that 100 megawatts with the battery and what battery behaviors they want, if they want it to charge or discharge, what they want to do on that. Hybrid resources are expected to follow their dispatch. So they're expected to follow their DOT at all times. Where co-located resources, we have a VER component, then that forecast goes directly to the market optimization. And the renewable side of the co-located can follow the VER dispatch rules. So they can produce as capable during certain situations for the forecast. The battery will be dispatched and the state of charge will be managed. I know this was a question from the earlier panel. The CAISO does do state of charge management. There is an energy storage initiative that's going on right now that's working to enhance that and improve the state of charge management that's going on in the system. But we do that for the co-located resources. So one of the things that has to happen with a co-located resource is an aggregated capability constraint. And so you have two resource types behind the scenes of one point of interconnection, which is a POI. And so what we've done is we've created an ACC or an aggregated capability constraint at the POI. And oftentimes you see that the POI, for this example, is 100 megawatts. And then behind the scenes, you have a battery resources at 100 megawatts, and you have a solar resource that's 50 megawatts. So both of these cannot put full output onto the system at the same time, because then you're going to be above your point of interconnect, and that's just a no-no. So with that, the market uses this ACC to make sure that it's co-optimizing underneath the hood, each one of these resources to stay underneath the aggregated capability constraint. Effective in 1215, one thing to note is that these have to work together in the market optimization. So one of the things that happened when the tariff went effective in December of this past year is if this battery resource is qualifying for ancillary services and it's holding back for any market instruction, it's a requirement that the solar resource has to follow its DOT during that time, because we have to ensure that this resource, if it has to dispatch for regulation, it has the ability to dispatch for regulation and make sure that we're holding to the POI constraint. So there is an optimization going on in the market to make sure if this resource has ancillary services on it, the solar resource has to follow its dispatch more closely during that time. All right, let's get into forecasting a little bit. I'll get to the end where we asked for a new data point. And this is really to talk about why. Why did we need another data point to feed into demand or into the load for, not the load, into the renewable forecasting for both solar and wind resources? So one of the studies that we did was to really look at a set of resources that were co-located As you saw, the co-located resources came on the system first. So we've been able and had time to analyze them a little bit more in relation to the error that they have. What we found is co-located solar resources error was 2.5 times higher than a traditional solar resource. So the question now is why? Why are we seeing that the co-located resources have a higher error? One of the biggest reasons that the co-located resources had a higher error is in relation to the data you get from them. They are dispatching for the market more often. So they have telemetry where their demand actual or their solar actual. So say that their forecast could be 100 megawatts, but they were providing 50 megawatts of supplemental dispatch. So economically, the market said, hey, I need to bring you down to optimize the system. Their telemetry actuals coming in at 50. Well, for the forecast provider or any forecaster to train that in, you can do that in different ways. But one of the things is you're limiting the amount of data points that you have that have no estimation. You can try to back into them, but you're limiting those data sets to train the models off of. We were seeing that that was overall impacting the forecast accuracy for these resources. So that happened on both sides of the house. It was something that we watched and really led us to needing to require an additional data point, which is called the high sustainable limit, or HSL. Visually, I love seeing graphs. I think numbers are really cool to tell a good statistical picture, but I really like to know what is going on underneath the hood of the shapes of these resources. So this is one co-located resource that we have on the system. The orange line is its maximum capability. The green line is supplemental dispatch or economic dispatch that the resource may be doing for whatever reason. The black line is the RTD market sent forecast. There's different ways that that can come out. So this is what hit the market during that time. Red is actual, and then the gray line is the dispatch that the resource is receiving. So you see for this particular resource on this day that it had some really big supplemental dispatch where it was taking the resource from its actual and then sending it down to zero during certain time periods of the day. This VER actual, I do want to note, one of the things that we monitor is the actual the resource is putting out plus the supplemental dispatch, because we want to monitor the accuracy of that full fuel forecast, not the accuracy of the market optimized forecast all the time, because of the fact that when you're trying to look at the vendor and see, well, what performance the vendor did? Well, the vendor did pretty good right here if the resource telemetry did not go to zero. So I don't want to compare the vendor accuracy against, this zero that the DOT was versus where the actual would be. So why was the market dispatching this resource down? Well, we'll add a couple more lines. So now you have in dash the battery resource that's under the same aggregated capability constraint, and then the battery awards that were happening from the market in combination to the DOT. So that you can see specifically in these instances, the market wanted the battery to move, and it needed to make sure it was honoring those point of interconnection constraints that were on the system. And so by doing that, it said, hey, solar, you drop down, battery, you move up, but I'm still going to hold the market at its POI, which was 100 megawatts. So you do see them working together very well within the optimization of the market, even though they are two single resource IDs. So the high sustainable limit. So this is the new telemetry requirement that is out for the California ISO on all hybrid and co-located renewable resource types. So the HSL, a lot of people come to me and be like, was the HSL a forecast? And it's kind of hard to say, because a forecast from a forecasting perspective, it looks farther in the future. Like, what is the output of the solar going to be at 2 o'clock today? That's where you see a forecast. this is more of a telemetry point that has some calculations behind it to tell us at this moment, solar resource, what could you produce if you weren't being dispatched from the market? So if your actual's down at 0, what was your capability based on the inverters that you have on the system and the weather that's out there to get to a data point? And so we're really trying to eliminate the market actual impact and then increase the data sample that the vendors have to do training off of, as well as the big thing is the California ISO, and I think I've done this in other presentations, has a persistent model that's in-house for our renewable resources. And that persistent model can be used on HSL and it can stop us from flipping back and forth. So right now, if persistence is based off of the telemetry actual that happened the previous time period, whether it be 5 minutes ago, if that was dispatched for the market and the telemetry actual went down for the market, at the time we have to switch to the external forecast service provider intentionally, because it's critical that we keep the full fuel forecast out there for the solar resource. And when the HSL comes in, we don't have to do that flip as much, because as you can see on the graph over here, the actuals in red may be moving around, but the HSL value that's coming in is closer to what the true capability of that resource is, taking in outages, inverters, and all things, so that we could keep on persistence and help improve the accuracy of not just the training sample that's used, but also the RTD market optimization. This is an example of using HSL in a wind forecast as a point on a particular day. The red is flipped. Oh boy, I always do red as forecast. I flipped it. So red in this one is forecast, just to confuse everybody, including me. And then green is telemetry. So you can see that when you put in the telemetry, and this is the persistence created using the HSL point, you can see that you are able to help the persistent forecast overall to help follow what is actually happening in the system. Like, this is the part that I really highlight right now. When you switch to the vendor, still doing a really good job of trying to chase the ramp that's happening here. But what we see with persistence is oftentimes it helps us get closer to the ramps that are happening on the system. So by using HSL, it allows us to get closer during some of these heavy ramp periods that are on the system. And this is my last slide. This is just a suite of products that the ISO has been working on to advance the high penetration of renewable resources. I know we talked a little bit about some of these in this presentation, but one of them is we did bring in an in-house persistent forecast for our large scale wind, solar, and now co-located resources. That was done a few years ago. We've integrated forecasting for both hybrid and co-located resources. We implemented multiple renewable forecast providers. So we have 2 forecast service providers on the renewable side, and we optimize which one is better for differing conditions, whether that be different time periods or different weather conditions. So we have the flexibility to move around to make sure we have the most accurate forecast going to the market. On the demand forecasting side, we have rooftop solar behind the meter forecast and actual provider. And then we're feeding raw numerical weather prediction models into the demand forecast. Specifically, the HER is really critical for us right now because of its smoke parameter. As you guys know, California gets lots of smoke now. We have a smoke season, I call it, at this point in time. And that's the one that accounts for temperature based on the smoke, as well as some of the smoke fields. So it is critical to have some integration to the demand forecast off of that to help with some of the error that we were seeing. There's uncertainty products that we've put out as well that are optimized off of the risk that we want to take on the system for the uncertainty that comes with the renewable resources. At the end of the day, and I know both Aidan and Erik talked about it, yes, we want the point forecast to be as accurate as possible. there's really no standard. 0% would be totally acceptable because then we wouldn't need these other products, but realistically, that's not probable. So we started developing products to handle the uncertainty that's on the system. And there's really a suite of them that goes from the day ahead timeframe all the way to the real-time timeframe to make sure that there's two pieces. One, we have extra megawatts committed to handle the uncertainty that may come in different conditions. And then also there's different risks we want to take on based off the day that's on the system. So for regulation requirements, as an example, if we know that there's going to be a really variable day on the load, solar, renewable net load fleet, we may not want to take on a 95th percentile risk. And we may say, no, we're going to go and protect ourselves to the 98th percentile to make sure we have enough megawatts for operations to handle whatever is to come their way. And we move that lever really based off of the forecasted conditions that are coming. And with that, I am done.
Great. Great talk, Amber. Let's just take a step back. And I mean, if your head is spinning from all this, all I can say is join the club. We all look at this and this is such a complicated space, right? This intersection of forecasting and the markets and the system operations, reliability and all this sort of stuff. So it's totally normal. I mean, don't at all feel shy about asking questions and having a robust discussion this week, because this is what this conference was for. We started it way back in a very cold February in St. Paul and said we have to bring the meteorology community with the grid operations community, and it's been a very useful event. But what we're seeing here, I think that even adds other complexity when we get to discussing storage and hybrids, is arguably an inflection point where it's really likely to change the markets, the whole way we actually operate our system, the real-time operations, everything. Because, take a look at storage, take a look at hybrids. We designed the system for conventional resources 25 years ago for our markets, and we've been operating, the utility's been operating this grid for 100 years with the assumption that they knew that, well, this is a coal plant, so it does this, or this is load and it does this. And now you got something like storage and hybrids. It's not purely a generator. It's not purely a load. It acts like transmission some of the time. All the silos are gone, right? They don't really work well. So we get into a lot of complexity in the RTO ISO discussions around North America here about how do we deal with this next thing, right? It's always adding more and more complexity, right? And the issue is really, when does this become the straw that breaks the camel's back, or when do we need to make it be somebody else's problem or abstract it differently, right? So I think that's what we're looking at. It's a very important thing now as we bring in load participation and DERs and, first of all, just a word on me, I am a broad guy. I'm not a deep, specific engineer that specifies, focuses on anything. I was running WinLogix, pretending to be meteorology a few years ago, and got it. That company got acquired by NextEra, the largest developer of renewable projects out there. Now I'm actually not even part of what's become NextEra Energy Analytics, which was what WinLogix is today. I'm actually part of the regulatory team to help out because these technical issues are becoming so critical to the deployment of our renewables, of our storage, of our products these days, that it's these interfaces with the markets, with NERC, with FERC, with reliability, with resilience that really move the needle for us, right? And it's a very complicated time. All of our heads are spinning. We don't have enough people. We don't have enough time. There's no way to keep up. So it's been very interesting for me as a generalist from the technology and software side to take this on. And I'm also the kind of guy that, as Amber and Erik know well, I really like to get people to think outside of the box. So I'm not going to hesitate to throw out crazy ideas sometimes just to spur the discussion about why are we still doing it that way, or is there a better alternative that would be a more elegant solution? Because I've learned, I was designing large software systems several decades ago, and had a great partner who was a brilliant guy. And you throw out this great concept, I really would like the system to do this. And Bruce, my partner, would intentionally not respond to me for 2 weeks. And then he'd come in one Monday morning and he'd say, hey, that complicated thing you wanted? Well, I thought about it. I finally figured out how to do it in 8 lines of code. So here you go. But he wasn't going to do it until he found an elegant solution, right? And so when I look at exploding complexity, my first reaction is to say, what's the right perspective that would make this problem simpler, more elegant, right? So I get really hesitant about just adding patch on patch on patch. Now with NextEra, huge company, half of it is Florida Power and Light, the other half is NextEra Energy Resources that I work with, which is an independent power producer, meaning we're one of the largest developer, owner, and operators of the renewables and storage hybrid plants out there, often selling that product to other utilities or to a Google or somebody like that, right? Huge fleet, a lot of experience with this. We have to operate in every one of those markets that Erik showed you on the chart that has their own set of rules, their own set of acronyms, their own set of meetings. Full-time jobs for dozens and dozens of people just to try to keep up with this, right? And California's done a spectacular job, I think, with storage and hybrids. They really embraced the idea as we have been kicking it around. They did a lot of great work on it. So I'm not at all saying that this is bad, that the RTOs are all kind of going their own way, but it adds a lot of complexity. And then we have FERC kind of saying, well, step back, what are the rules here? What's the general concept? What do we want to do next? So it becomes a real system design and especially a system maintenance problem to keep all this held together. So with that kind of as background, NextEra has really embraced this and actually gone beyond this already. In some of our quote hybrids, we're actually putting in data centers behind the point of interconnection down in Texas, right? We're putting in hydrogen electrolyzers. We're putting all sorts of things that are some variant of load or generation or whatever. And we're finding it to be more practical for a lot of reasons to want to put this inside this hybrid, but behind the point of interconnection with the grid, because the grid is only part of the services this is providing, right? And we're going to be putting in all kinds of other stuff. So it does not fit the mold even more, in some cases about, would that be co-located? Would that be the general concept of a hybrid? It's quickly evolving beyond that, right? Because the goal of NextEra really is to look at decarbonization services more broadly. And we've been looking at this issue about how do you put together a bid for a hybrid or co-located resource? How do you put an offer to the market, for example? And then, if you're awarded some service, then you get into this issue that Erik brought up, very valid about, how do I avoid infeasible dispatch if you're asking me to do several things at once? How do I prioritize that? These are really complicated problems. There's a software package that's been called Optos out of NextEra Analytics in St. Paul, and Sam is here from the group there. We have, we've been looking at this, but we're also looking beyond that and saying the customer really wants these services. They want to totally decarbonize everything they do in their company on an hour-by-hour basis. How do you do that for them most effectively? Through some combination of contracts for new plants, market purchases. They become a market participant in a way here, one way or another. How are they going to make their offers? How are they going to do this? But it's really already going to a higher service level. This whole issue about decarbonization as a business model. And we kind of we need to make that step eventually. We're not just in the electricity business anymore. The grid is the primary vehicle for decarbonization of all energy in society, right? So this is a critical piece, but it's quickly getting very, very complicated. So when I look at this complexity, as I pointed out, being a software guy, I say, what's the right architecture for this, right? Erik mentioned the universal participation model, which was a direct early outcome of my background as a software designer, where I said, look, you have this service that you need done by this function or this module or this intelligent agent. I don't want to write 10 of them that are almost the same. I want to parameterize it and say, look, you know how to do your core function. Here's a set of parameters, and I'll just call you the way I want you to do it, but I only write and maintain it once. right? So you don't want this proliferation of participation models, because we could very quickly, with the pace of innovation, now that everything is digital, power electronics and so forth, I often say that you give me enough energy, software, and electronics, I can make it look like any machine you want at the point of interconnection, right? So it's partly it's a reflection of the technology components within it, but also it's a reflection of how much software do I want to put into it, and in a sense, how much electron inefficiency are you willing to sacrifice to make it look simpler, right? And we're very hung up in the power system so far historically with complete optimization that the ISO RTO, as part of the unit commitment and dispatch process, should be able to take essentially a lot of the almost bare iron resources I give you with traditional generators and figure out how to maximize everybody's benefit from those, right? That you'll tell me when to start my unit and how to get the most out of it and how to make the most money for me, and you're able to do that. I'm letting you kind of control my equipment for that end, because we all come out ahead. If we've got a whole collection of pretty stupid resources that just produce a lot of cheap energy, I can put that together into a very valuable service to society and maximize the revenue to all. Makes perfect sense until the complexity gets more and more and more, and we get into these sort of, where is society forcing us to go with this? Is that sustainable? Is that computational, right? So I threw out the universal participation model saying, well, that's how a software architect would do this. But if you put all that into our unit commitment and dispatch software and you want to run it every 5 minutes and you want to optimize for dozens of parameters simultaneously, it quickly may not be computational even with the latest cloud computing, right? So really, when we started talking, a group of us started writing some papers about this concept of a single resource hybrid. That was a reflection of saying, let's go completely the other way. Put all the complexity inside the market participant, right? Inside the hybrid. Efficiency, maximum efficiency of the electricity, of the electrons, is no longer the objective. The objective is that I want to know exactly what services interface I have with the rest of the grid. Then you can tell me what services you really need, and I can use my innovative power inside a hybrid with all this energy storage, software, and electronics to give you the highest value services you want. And by the way, almost all the time, because wind and especially solar and now storage really are technologies on a rapid learning curve that are getting cheaper all the time, unlike commodities like fuel-driven resources that are really driven from the commodity prices and are going to go up. The renewables are going to get cheaper and cheaper and cheaper. I'm going to put more and more and more of them in, far in excess of my injection limit at the point of interconnection, right? Why would I not? It gives me so much more flexibility, so much more capability, right? So in other words, I'm no longer going to, in my future, we're no longer going to be limited by energy. It's all about services, right? And by the way, I want to control probably my own batteries and my own components. And I want to be able to upgrade that almost at will. I want to be able to put in the newest version, the next generation of the batteries or the long duration storage in there, because then I can provide the services with more certainty, lower risk, and pursue the highest and best value for this. So it's really this trade-off behind, am I willing to give up the efficiency of maximal use of every electron for the freedom to innovate inside my own resource, right? It's a different model. It's very foreign to how we've been thinking about running the grid, because it's, in a sense, it sounds almost like the great benefit of going to large markets. We gave up all those small balancing areas, right? Now I'm kind of having to manage that inside every resource. But I would argue we're at the point where we got enough technology and enough cheap electrons that actually that's no longer a stupid thing to consider. And at least some people are going to want to go that way. It's an arguable position, but I think it's at least something we really ought to be thinking about, because society may continue to surprise us as it's done in the last few years. And come the 2030s, we could have some really dramatic changes here that we have to get ready for that could break the straw that breaks the camel's back in our traditional way. I agree, though, with Amber that there are certainly challenges, and Eric's pointed out a lot of valid points here. There are challenges to just being a resource that just completely makes just a single offer. There are clearly some inefficiencies in that, the way we think about it other ways here. Amber pointed out that the co-located is still the more popular resource so far, because we're starting out with relatively small batteries and often adding them to existing solar plants, more or less. And we're at an inflection point there too, where we came up with these very innovative ways, and Erik was instrumental in some of these on, because wind and solar are fuel-driven resources based on a variable fuel source, we shouldn't really penalize them in the same way for failure to follow dispatch. In a sense, and unless the system is constrained, we'll take that extra clean energy, or if the cloud goes over, we understand you can't do anything about it. So you give a variable renewables, that's sort of, basically it's just a waiver from the imbalance penalty of the failure to follow dispatch in the real-time market, right? Makes a lot of sense when you step back and think about it. Now I add a battery to it. I don't really want to give that up. It's just a small battery. So there's real problems with this transition. But as Amber showed very well, a co-located resource is not simple, because if I keep adding more technologies in there, or I oversize those things even more, or I put loads back there, then how do you deal with that constraint that you're creating at the injection limit, which is smaller than the sum of all the parts behind there, right? And the way they're doing in California is good, but okay, what if those different pieces are under different contracts owned by different people for different reasons? It can very rapidly get really complicated, right? So it's not a general solution. It's not a panacea to just be co-located, is all I'm saying. So, there's a lot to talk about, but I'm a huge believer in markets. I also totally agree with Erik's points that we're looking at some of these future services, some of which would be good market products and some wouldn't. Some of the market products out there that I think we've been experimenting with, like some of the ramping flexibility products or uncertainty products, I can see why we want to do them, but I also get really concerned that they actually, in a sense, suppress the variability of the real-time spot price, which is supposed to show us scarcity in other ways. And here I've got all these super fast electronic resources now coming online that can respond within seconds to a scarcity price signal, but we're not really encouraging them to do that, right? It's a real interesting debate, I think, about what's more important. We want to keep the real-time operator comfortable that they got enough energy for these future periods with some sort of look-ahead dispatch in a way. I get that, but if we're going to be in a market, I'd like to say, follow the spot price in the market. It is not a sin to actually respond to price. That's what we wanted load to do all along. Now we've got these super fast resources that can also do that. So, if we're going to have markets, I would expect to have price response, give them that signal. If we want to do it through contracts and other stuff, that's fine. And it will vary. But I think it's just a fascinating time when we look at what we're doing with market design and changes and the exploding complexity. And really, it becomes for me a question about whose problem should it be? Should we have more analytics on the part of all the market participants where they manage these own resources and they interface with the system at a higher service level? Does it essentially start looking like the web of thousands of intelligent agents that are able to do this analytics and software and do that? And I tend to think it will over time. Or do we try to kind of stick with the current model of more of a top-down command control that you tell me what the pieces are and I'll assemble them and dispatch them and coordinate them, which has its validity. I just worry about, do we want to stick completely with that, or is there some tipping point or at least some middle ground where we try to get the best out of both of these? Because what we're seeing is that the complexity of trying to continue to add patch after patch after patch to the markets to deal with this is getting pretty tough. And the pace of innovation is only going to increase now that we become these digital and electronic resources, right? So it's a fascinating time. It's the most multidisciplinary space we're in any industry I've ever been in my career, right? It's not just double E's, it's software, it's economists, it's meteorologists. It's talking about, society, how we're going to actually, provide everybody's need for electricity. Even if they can't have the latest electronics in their home, there's an obligation to serve as well. It's a fascinating place, and we need a lot of people in it. We need people that can actually think across the usual silos and come up with some really more holistic, broad-ranging ways of how these pieces are going to fit together. So I'll stop there, and whatever time we have left for questions.
Yeah.